Alright, so we're going to get started. Some administrative things first off. I've been sending out emails. It looks like I'm going to be sending out emails on the T days. And in it, I have a list of all the times that I'm doing the live chats. And so I've had some few questions about people saying they weren't able to get into a live chat. Attendance is not required, but I'm doing these live at the course times. That way, if you need to interact, it can help. And it helps me, actually, having the interaction in chat. YouTube is letting these videos stay stored, and they're accessible through the playlists. I've been giving links to the playlists, and have been putting the due dates up in Pearson. Now, the exam that we were supposed to have on Thursday of last week, a week ago, is on Pearson, and it is due next Thursday on the 9th. Now, Pearson has been having some issues because every school in the country, well, globally, has switched to online learning. Their servers are experiencing a heavier load than normal, and a lot of the load is in the evening. So they have been adding more server space using their AWS and virtual servers, increasing their server capability. That has required them to take parts of the site down, and it seems to be happening in the evenings mostly. It's much better the last couple of days than it has been. So I extended the due date to next Thursday because of that issue. I'm continuing to monitor it. The math department here has been monitoring it. Our department chair has been talking to the Pearson rep, but Pearson's been being fairly good about putting the information up at the top of the web page. It has caused some really annoying issues, though, with like kicking people out or not saving work coming across. And so I'm aware of that, and we're dealing with it as the best we can. We've got to be a little bit flexible. In the emails, I have put a link to the playlists. The playlists for both the 097, which is the augmented course for this that not everyone has, and the 162, which is this course directly. These lectures will be in here, and worked examples of particular problem sets I will put up. We're now firmly in new material, so I'll be doing more examples as I go. I was playing some catch-up, getting review material in for Chapter 3, so you'll see some short videos that tend to go around the questions people ask in email. Please, if you have any questions on the homework assignment, I have posted the homework for sections 1 through 3 in Chapter 4 of the textbook, which gets us through polynomial division. Email me a question, take a picture of your work on your paper, and we can look to see what we can do. I can always record a video example of a particular problem, or I can help hunt for errors. If you watch the previous lecture on polynomial division, I made a horrible sign error in one of the divisions, and 2 minutes in, 3 minutes, polynomial division takes a little bit, caught it and went back and corrected it. And I am a big fan of trying to do my work live, so that I can make mistakes and we can see how we can recover from mistakes. And sign errors are a big mistake in the type of stuff we're doing. But so, send me photos of the work you're working on, or if you can type it out in email. If you're in Pearson and you have a question on a particular problem, in the upper right-hand side there is a email my instructor this problem, and it will send me your version of the problem with the numbers you get. Pearson randomizes the numbers, so each one of you will have a different test, will have a different set of homework. Questions the same, the actual numbers end up being different. And so if you use the email my instructor, I get a copy of that. So I'm going to continue doing the T-Day emails of where we stand on what's due. I'll keep putting lists to the playlists, and I will try to put things up there. Blackboard and I are fighting. I think Blackboard has won, mainly because I have 4 sections of this class, and I have to enter the same thing into each of the 4 sections individually. It doesn't have a bulk upload that I haven't found yet. It's been my biggest complaint against it. And so I'm working on copying the material up there as I go. I'll put the PowerPoints up from where we are forward, and I'll include some of them back. I'm not a big PowerPoint fan for this type of material, though I'm going to reference the book's PowerPoints as a set of notes. All right, so starting for the first lecture today, or this evening, and I'm going to work my way towards polynomial division. We'll probably take a short break in the middle. I'll update the link, just so this video is divided into 2 parts. It's not one behemoth for the people that come in and watch it later. Now, in section 4.1, I described what a polynomial was, and we worked on kind of looking at behavior of a polynomial. In fact, I talked about a lot of the stuff that the book will end up talking about in section 2, and I'm going to go into that in more details. But in its most general form, polynomial function is a series of terms, and let me just write it here. Now, these lower subscripts are numbering. So this would be a sub n minus 1, a sub 2, a sub 1, a sub 0. And they each can represent a different coefficient, something that multiplies. And then I have the variable x from n all the way down to 0. And so notice I'm going to write my powers descending. And so an example of a polynomial here. I have 3x to the 4th plus 2x cubed minus 4x squared plus x plus 1. And so in this case, my highest power is n. And we would say, hey, this is a 4th degree polynomial. And the leading coefficient, a sub 4, the leading coefficient is 3. The constant at the very end is 1. And the leading coefficients and the constants we will find are very important. The stuff in the middle is important. It does the behavior of our polynomial functions, but we can get a lot of information we need from the leading coefficient and the terms. Now, what happens with a polynomial, and I'm going to use some of the parts on the slide here. Again, not a big fan of the slides, but we'll go back and forth with them, is that polynomials can have turning points. And so in this particular polynomial that we have a turning point here and a turning point here. There are 2 turning points. And what happens if we talk about the behavior of our function in its most general terms, our function in this case is increasing. It reaches the turning point and it begins to decrease. It reaches the other turning point and it starts to increase again. And so I could describe the behavior of this function that it's decreasing from -2 to +2. Right, it's decreasing here. And it's increasing it's increasing from negative infinity to negative 2, and it's also increasing from 2 to positive infinity. And so turning points are these places where it changes from increasing or decreasing. And a lot of the descriptions of what we can see with our polynomials are how it changes direction. Now, if we think back to what we were doing with our lines and with our quadratics, quadratic formulas had one turning point, and it was the vertex. And lines didn't have any turning points. One of the other things that we talk about is end behavior. And what happens with end behavior is what's going on as the function goes towards positive infinity or as the function goes towards negative infinity. What happens on the big ends? Oops, sorry, hit the wrong button here. And so this function, if I were to look very far away from it, it would appear to be going out towards infinity as x got bigger and going towards negative infinity as x got smaller. Let's make a graph of this here. 2 seconds. I think I have a graph approximation of this here. So I'll switch over to the graph. And we have a similar, if not exactly the same, function. But what I want to be able to do is, what I mean by big N behavior is I want to zoom out from it. I want to take this function and look at what happens as I get far away. So all the action in the function happens in this small area here between negative 3 and positive 3. We have this change of direction. But if I look very, very far away from this function, if I zoom out, it's almost a line. Right? That difference in the middle doesn't change much. And big N behavior tells us that. It tells us what's going on as we get far away. And so when the book talks about this big end behavior, or this end behavior, it's talking about what the function does as you get towards infinity or negative infinity. All right. Make sure I still have things centered on the screen the right way. All right. So we're going to go back and we're going to look at some of the functions that we have looked at before and that we've been building up. Now, keep in mind our end game is going to be, we're going to want to break apart the more complicated and large polynomial functions into smaller functions, or a collection of smaller functions. And so knowing the behavior of the smaller functions will help us. And we have the basic things that we need to build polynomials. We have constants, we have linear functions, and we have quadratic functions. Every other function that's higher in power can be broken down into a combination of those things. And that's going to be kind of our end goal right here. So our constant function, they say, hey, listen, we have f of x equals a. Well, I'm going to come back here and I'm going to look at this in terms of how we defined our polynomial function. So a constant function in this definition, so a constant function f of x is equal to a, and I'm going to say sub 0. Because if we look at it, right, I could, if I really wanted to be sneaky, put an x to the 0th power there. Because anything to the 0th power is 1. And so we can say this is a 0-degree polynomial. A constant is a polynomial with the least amount of terms, one term. And it has x to the power of 0, so the variable doesn't matter. And so the leading coefficient and the constant end up being the same thing for a constant function. It's a number. And if we come back here and look at what this is doing, since they gave us a nice graph of one here, here we have f of x, and in this case it looks like f of x is equal to 4. And we have a constant line. No matter what I put in for x, that line's on 4. Put in 5 million for x, I still get 4. And over here, I have f of x equals negative 3 as my constant function, polynomial function. Now, there are some things about this. Notice it has no turning points. A constant function never turns. It also never intercepts the x-axis. Even if I had f of x equals 0, which would run along the x-axis, I'm not going to say it intercepts the x-axis, because intercept means you cross the x-axis. You have to not be on it, and then you get to the other side. And if I'm always on it, I'm not intercepting. And so we can say these constant functions have no x-intercepts or no turning points. The next polynomial function that we looked at was our linear polynomial function. And here they're writing it still in the linear form, f of x equals a of x plus b. In fact, I find this nomenclature here a little odd. We said m of x plus b when we first studied these, where m was the slope. Well, let's look at this purely as a polynomial. So I'm going to come back here. And we'll look at a linear function. Let me change colors again. And so a linear function, if I'm doing the same nomenclature that I have from up here, I have a sub 1 x to the first plus a sub 0, and I'm not going to write the x to the 0th power. And so this would be a first degree polynomial. And the leading coefficient is the slope. And our constant is a sub naught. And we spent a good deal of time looking at our linear functions and how they describe rates of change, right? The slope could be the rate of change. And we pulled them across. Well, now we're going to look at some of the things that come out of this in the context of general polynomials. And so the graph is a line. It's neither horizontal or vertical, right? Because a horizontal line has m equals 0. And if you have m equals 0, this goes away and it becomes a constant function. And a vertical line has m undefined. And undefined lines couldn't be a function because they failed the vertical line test. It has one x-intercept and no turning points. So if we look at a line, it crosses the x-axis in one place. Oops, this keeps trying to Let's see if I can do this without it making a line. All right, we'll go here. All right, so there we cross the x-axis at one point. Yep, nope, it still wants to make a line. Now, I will just not use the pen on that. My apologies. it crosses the x-axis in one place. And it crosses. It is on the one side and it ends up on the other. And the place where it touches the x-axis before it crosses over is called the x-intercept. But that only happens once. And lines never turn. They have the same rate of change always, and they continue off. This one starts down in negative infinity and moves up to positive infinity. Well, this one starts at positive infinity, and as x gets bigger, goes down towards negative infinity. So its large N behavior is to move at a constant rate of change towards infinity, be it positive infinity or negative infinity. In fact, the slope, a sub 1, if it's greater than 0, or if it has a positive slope, means that it will go towards positive infinity as x gets bigger. It'll go towards negative infinity as x gets smaller. And if my slope here is less than 0, it will, a sub 1 less than 0, it'll go towards negative infinity as x gets bigger, and it will go towards positive infinity as x gets smaller. And so this is behavior we had for all lines. And that's what it's trying to say here, is the N behavior matches really the sign of the leading coefficient. If a is positive, as I go towards positive infinity, I stay positive. If a is negative, as I go towards positive infinity, I go towards negative infinity. And so the sign of the leading coefficient describes the behavior of the function for us. All right, and here is what we were doing in Chapter 3, quadratics. Again, we used the A, B, C because that worked nicely with our quadratic formula. All right. And so identifying what each coefficient was gave us ability to find a solution when our function was equal to 0. All right, the quadratic formula came out. So identifying each coefficient was very important. But what we're going to do here is we're going to continue back. I'm going to scroll down just a little bit. And we'll look at a quadratic polynomial function. And again, I'm going to continue using this generic nomenclature for polynomials, where I'll be talking about my coefficients in terms of the degree, and my powers of x will be descending. So quadratic, the leading coefficient, I'll put a sub 2. X is to the second power. X to the first power. And then in my constant. And we say this is a second degree polynomial. Now, the leading coefficient here didn't describe the slope, but it described if my parabola was smiling, right? We said if the leading coefficient, if a sub 2 was greater than 0, right, which is positive numbers, so if a sub 2 is positive, then my parabola was concave up and it was smiling, right? Smiley parabolas are positive. And if a sub 2 was less than 0, my parabola was pointing down, or negative. So, smiley parabolas had a positive leading coefficient, and frowny parabolas had a negative leading coefficient. And so this behavior we can use to describe are second degree polynomials. And so what we want to do is we want to look at that behavior across all of the polynomials. And so we'll look at these three examples here. This a sub 2 is greater than 0, but notice it has no x-intercepts. And I've been trying to prelude to you or foreshadow that when we cross the x-intercepts, those are going to be called zeros, roots, or solutions. And so we would say that this polynomial has no solution. Right? When we set f of x equals to 0, there are no solutions. When you don't cross the x-axis, there's nothing you can solve for on this. Now, we did find that, I'll be a little more specific, it'll have no real solutions. Because we did find if we put this into the quadratic equation, we would get imaginary results. For the second, this middle one here, a sub 2 is still greater than 0, and it's still a positive, right, parabola. But it's going to have 1. One x-intercept. And so it had one solution. It would solve to one solution. We put it in the quadratic equation, and the part that was the square root became a 0, and we would get the one solution. Now for this one here, a sub 2 is less than 0, and it has 2 x-intercepts, or 2 solutions. Now, I could have an a sub 2 less than 0 where I only have one solution, if I touch like that. I could also have an a sub 2 less than 0 where I don't touch. So the sign of this coefficient, the leading coefficient, tells me the direction I point. And then in the solutions are determined by, well, if I cross the x-intercept or not. But there's some things to note that happen here. So if my leading coefficient is positive, notice I come from positive infinity. I reach the turning point at the vertex, and I go back out towards positive infinity. Here I'm still positive. So I come from positive infinity, and I'm decreasing until I hit the vertex, which is a turning point. And I go back out towards infinity. So no matter what my function is quadratically, the leading coefficient tells me that on either end, I'm going to be going to the infinity with the same sign. If my leading coefficient is negative, I start at negative infinity. I reach the turning point at the vertex, and I go out to negative infinity. So the big N behavior of a quadratic polynomial is to go towards the infinity with the same sign as your leading coefficient. And that's what it says here, right? N behavior tends to positive infinity on both sides when A is positive, and tends to negative infinity on both sides when A is negative. And so our behavior of our functions changes based off the leading coefficient. What we have now seen between a linear and a quadratic polynomial, that behavior will keep repeating. And that repetition is going to show us something about polynomials in general. So we're going to look at cubic polynomials next, which are to the third power. And we're going to look at these patterns again. And we're going to try to generalize out of it. So I'll come over here to cubic. And now, Notice they're writing A, B, C, D for each coefficient. Well, I'm going to come back here and I'm going to write that in our new form that we're using with the A subs. I like the A subs because that way I don't have to worry about running out of letters. Right? If I have a polynomial to the 38th power, I don't have to go A, B, C, D, E's, and what do I do after I get to Z? So having something where I can put a new number in gives me, well, infinite things to put in. So a cubic polynomial and don't worry, I'm not going to make you do polynomials to the 38th degree. We will spend most of our time between cubics and things to the 6th power at the most. Most of the time cubics in 4th degree. The patterns that happen in 3rd and 4th degree continue on up towards infinity. And so if you can work with cubics and you can work with quintics and quartics, you're good. And the words quintic and quartic, I'll probably not say. I really do like saying, 1st degree, 2nd degree, 3rd degree polynomial. It just makes a little more sense. So a cubic polynomial has x to the 3rd power with coefficients descending all the way down, and the powers, right, descending powers of x. Now, a sub 3 is our leading coefficient here. And a sub naught is our constant. Again, keeping track of your constant and your leading coefficient is going to help. I have found that the book has a tendency that if the leading coefficient is negative, it'll sometimes write, like if this was negative 3x cubed plus 2x squared minus 4x plus 1, it'll sometimes write this in its opposite order to not put the negative sign out front. I will rework these so that I have my powers descending. I find that pattern for me is very visual to find the things I need to find, because I need to find the leading coefficient and its sign, and I need to find the constant and its sign. So keeping it in this order helps me organize the functions and what I'm going to do with the functions. Well, let's look at the pattern that we're going to see from a cubic function and compare that to the pattern we've already seen with a linear function. So the graph can have 1, 2, or 3 x-intercepts, and it can have 0 or 2 turning points. The end behavior is negative when x is small and positive when x is big if the leading coefficient is positive. If the leading coefficient is negative, it's the opposite. And it must cross the x-axis at least once. Let's look at this visually. This makes a lot more sense, I think, visually than stating it as a system of rules. So here I'm starting at positive infinity. I hit a turning point. And I hit another turning point. And I go off towards negative infinity. Now notice, if I start at a positive infinity and I need to go off towards negative infinity, to get between the two infinities, I have to cross the x-axis somewhere. And so this last rule, the graph must cross the x-axis at least once, is really coming from this idea that if you start at negative infinity and you end at positive infinity, somewhere you have to go through 0. And the opposite holds true if you start at positive infinity and you end up going towards negative infinity. Somewhere you have to go through 0. And so this rule here is really implied by the end behavior that's coming across. And so this function, I could say whatever this polynomial function is, I know that a sub 3 is less than 0. It has a negative leading coefficient, so it starts from positive infinity and works through. It has 2 turning points, and it has 3 x-intercepts. This function starts at negative infinity and works its way towards positive infinity. It has 1 x-intercept, and it really has no turning points. This is a point of inflection, and we'll look at inflection points a little bit more. This function, if I hit my pen down too much, it turns into lines. Oh well. This function starts at negative infinity, goes off to positive infinity, and it has 2 x-intercepts and 2 turning points. So the rule that I hope we're starting to see is this function is cubic, so n equals 3. So at most, I will have n x-intercepts. And at most, I'll have n minus 1 turning points. And I talked about this a little bit in the previous lecture. And so this pattern builds up. It was the same for a line. A line was n equals 1. It crossed the x-axis once. And it never turned. It had n minus 1 turning points. And if we look at our quadratic is n equals 2. At most, it can cross the x-axis twice, and it has 1 turning point, 1 vertex, which is n minus 1. And the cubic function does the same thing. It has, at most, n intercepts, or 1, 2, 3, and at most 2 turning points, which is n minus 1. So the behavior that we have in a line seems to match what's happening with cubic functions. Cubics can turn, so we can get some extra x-intercepts and some turning points, but the big behavior is still the same. Goes from negative infinity and ends at positive infinity, just like a line does. So I'm hoping that my 4th degree functions will be similar to quadratic. And so we're going to look at a quartic, which is a 4th degree. I'm going to do the same thing. I'm going to go back on the blackboard, and I'm going to write this in our new notation. And we're going to then look at the coefficients that come across. So, quartic functions. Quartic polynomial functions. I have f of x is equal to some coefficient, x to the 4th power, and my degree of my x gets smaller, going from left to right. And so we say this is a 4th degree polynomial. I'm going to pull it up here. And so my leading coefficient is a sub 4. And my constant is still a sub naught at the end. Well, if the assumption that this is going to work like a quadratic is happening, then if a sub 4 is greater than 0, I'm going to start at positive infinity. I'm going to have at most 4 x-intercepts. And at most 3 turning points. And as I move, as x increases, I'm going to end at positive infinity. I'll make that as x increases. If the leading coefficient is negative, I'm going to start at negative infinity. And as I work my way out, I'm going to still end at negative infinity. The end behavior is going to match the leading coefficient. That's if this pattern of matching the quadratic would come about. It's still going to have at most 4 x-intercepts and at most 3 turning points. So let's look at it here. Right, it can have up to 4 x-intercepts, up to 3 turning points. Its end behavior tends towards infinity on both sides when a is positive and tends to negative infinity when a is negative. Well, let's look at them. Well, they kind of make, like Elvis-style smiling faces, right? It's got that little sneer going on. Or Billy Idol. Those are the last 2 sneers I know. I don't know anyone else that kind of did that lip curl, right? But you have these turning points and these intercepts coming through. And so in this case, a sub 4 is greater than 0 because it starts at positive infinity and it goes out to positive infinity. In this case, the leading coefficient is negative because it starts at negative infinity and goes out to negative infinity. And also here, negative, because we start at negative infinity and go out to negative infinity. And so something is happening that first degree functions switch between negative infinity and positive infinity. Third degree polynomials switch between negative infinity and positive infinity. Right. While second degree polynomials and fourth degree polynomials end up leaving at the same infinity as whatever their leading coefficient is. So I would say this has to do with the n being even or odd. And so we want to explore that behavior of if the polynomial is even or odd. And so the book goes through and looks at a quintic function, which is to the 5th power. And we're just going to look at the quintic graphs really quick. And we're going to see starts at negative infinity, goes out towards positive infinity. 1, 2, 3, 4, 5 x-intercepts. 1, 2, 3, 4 turning points. So we have a pattern where the odd functions tend towards both infinities and the even functions tend towards one infinity. The number of x-intercepts is at most the degree of the polynomial, and the turning points is at most 1 less than the degree of the polynomial. And these are important things that hide underneath. So let's look at my quintic here. See if I can get this quintic on. Apologize, the quintic's not showing. Ah, there's the quintic showing. All right. Ah, there we go. Let's come down here. And I'll scroll down. It's jumped up. Get some clearing space. All right. And so we can say that the degree of the polynomial classifies its behavior overall. And what I want to talk about is what we mean by big N behavior in general. and how the leading coefficients tell us what's going on. So I'm going to make a generic polynomial here. So I'm going to have a to the n, x to the n, plus, I'm going to have loads of stuff down here, and I'm just going to come back to the square term, the linear term, and the constant. And I'm going to start first with if n is even. And so what we mean by big N behavior is we want to be somewhere out near infinity. So let's say, and I'll give this some real numbers right now, we'll say n is even and a sub n is positive. And so we want to look at this behavior. We'll make an example of this, but this can work for any of these. So I'm going to say a sub n is positive 2, and we'll go x to the 6th. And I still won't care what's happening in the middle here. I will just talk about plus 3x cubed plus 4x squared plus x minus 10. All right. There's stuff in the middle here, but we really want to see what happens when we're near infinity. Well, if I get near positive infinity, so near positive infinity, well, let's see, 10 to the 10th, right? That's a big number, 1 with 10 zeros. So 10 to the 10th, well, 10 to the 10th to the 6th power is going to be 10 to the 60th power, right? This turns into a really big number, a much bigger number as I come through, multiplied by 2. If I come out here, 10 to the 10th cubed is 10 to the 30th. Well, this is so much bigger than this that this doesn't change that value too much. In fact, the only thing that could subtract it down here, this negative 10, is so small that as I get towards infinity, this starts taking over everything. And so when we're talking about the big N behavior, what's happening is as I get closer and closer to infinity, because this power is so large, these numbers get so much larger that we can't even see this number in all the zeros. So if I wrote a 1 with 60 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 20. Well, there is a 10 with 30 zeros, and so, or 1 with 30 zeros. So if I repeat that, that's what my leading term is doing. And so if I add something with a 1 right here, well, that doesn't make a huge difference to this. And so big behavior, and why we focus so much on what the sign is doing in the leading coefficient, is as I get closer to infinity, all this other stuff doesn't matter as much, right? If I'm over here and I have the x to the 1st, and I'm out here and I have x to the 6th, right? When this reaches a x to the 2nd, I'm already at a trillion, right? So if I had $1 trillion and someone's telling me to worry about the $1 bill over on the other side, I'd be like, do whatever you want with the $1 bill. I want to stay over here with the trillions. And so that's what happens with our powers, is these numbers get really small. And I should say, what would make this a trillion? That would be 10 to the squared, would make that to the 12th, and the 12th would be in a trillion. So if I had $1 trillion out here, this would only be making it to 100, right? And I wouldn't worry about a one Benjamin Franklin out of trillions. And so that's what we mean by big N behavior. Well, anything to an even power is always going to be positive. Okay? -1 times -1 times -1 times -1. Well, that's -1 to the fourth. A negative times a negative is positive. A negative times negative is positive. The whole thing becomes positive. So even powers will always make x positive. So the sign of the leading coefficient determines which infinity it's going to hang out with. Odd powers keep the sign of whatever you give it. And so that's why odd powers can cross 0. When x crosses 0, their signs flip. And so the coefficient in front tells me if I am going from negative infinity or going from positive infinity. And so that's why there's a split between the even-powered polynomials and the odd-power polynomials. And it has to do with what's happening out in front in the largest term. And so the book puts this together into some rules for us here. And it says that the graph of a polynomial function of degree n, where n is greater than 1, has at most n x-intercepts. And this word for us is going to become solutions, roots, or zeros. And so this is going to be really important, is if I have a polynomial and I need to solve it for something, this is going to tell me how many solutions I might have. And the might have part, those imaginary numbers come back up. And if I allow it to have imaginary solutions, if I allow it to have things that aren't real numbers, then I'm going to be able to say that a polynomial of degree n has exactly n solutions. Some of them might be imaginary. And so that's where we're going towards with all this. And then n, well, if I'm crossing the x-intercept 3 times, I have to turn twice to do that. And so when I say one of these, I get the other one for free, right? If I'm going to cross the x-intercept 3 times, well, to cross over a line 3 times, I have to turn twice. And so that's where they come from. So I don't like to see these as arbitrary rules, right? Because they all fall about from the behavior of the function. And here we're graphically looking at it. If it's an even degree and the leading coefficient is positive, it always ends up at positive infinity. If it's an even degree and the leading coefficient is negative, it always ends up at negative infinity. If it's an odd polynomial, if the leading coefficient is positive, it starts at negative infinity and ends at positive infinity. If the leading coefficient is negative, it starts at positive infinity and ends at negative infinity. The interesting stuff happens in the middle where it crosses and where the intercepts are. But the big behavior, as I get out towards infinity, when those numbers get so big, also tell me something on the behavior of my function. And so we can look at a graph of a function and get an idea of what might have caused it. Now remember, a graph of a function might be something we create when we know the function, but the opposite can happen. We can get data in, we can plot our data in, and we can look at its behavior. And as we were looking at the extrema, when we have these local max and mins, these turning points being extrema, or these local maxes and mins, we might be able to see that coming out in our data. And so if we can get some behavior from this, we might be able to build the functions to predict our data. So this is a two-way street. You can start with a graph because you've measured data and you've plotted it. you've plotted the points out, or you could start with a function and you could plot the points to see what the data is going to be. Remember, most everything we do in mathematics is reversible. We tend to talk a lot about functions creating graphs so we can see the behavior of functions, but the same thing can happen. If I have data and I look at the data points, I can describe the behavior and look for functions that describe that. So if I look at this function, I notice 1, 2, 3, 4 intercepts. And I've noticed 1, 2, 3, 4 turning points. Now this intercept is just touching. So the turning points become my clue. The 4 turning points means this has to be at least n equals 5 because it has 4 turning points. So if I were going to model this, I would want to look at something that has some coefficient x to the 5th power and then in other terms out here. Now that leading coefficient is going to be based on what's happening. Well, I start at negative infinity, or positive infinity, sorry, and I leave at negative infinity. So this leading coefficient has to be negative. And that's what this behavior will help tell us. Well, that gives me enough that I could start trying to figure out what function to make for this. In fact, having these intercepts, we will find, will let us build functions. And so there are 4 turning points and there are 4 intercepts. Because it rises, let's see, a is less than 0, sorry, went to the wrong screen there. You get to see my pointer, I didn't for a second. The left side rises, right side falls. There's 4. A is less than 0, or A is negative. That leading coefficient was negative. And it has an odd degree because it's crossing 0. And with the 4 turning points at the least, it might be degree 5. All of these things are related. They're behaviors that are all related to the degree of the polynomial. The degree of the polynomial is going to give us all of these behaviors that might happen. And that's going to help us solve things coming through. All right, so what we want to do here is we're going to graph a function. Now, how I want us to graph functions, and I gave out a worksheet before spring break on using Desmos, the free web browser utility. I'm going to repost that to Blackboard and make sure that we can work on this. Having a graphing utility makes a lot of this easier for us. And we live in an age where calculators and computers make graphing a lot easier and putting in points. We should do a few by hand. You should always do first couple graphs of a particular function set by hand. A lot of these things in the book, you should do at least 1 or 2 by hand, plot some points just to get a feel for it. But at the same time, we can use our software to see what's happening. So I'm going to take this function, I'm going to put it into Desmos. So let me come back here, go to my graphs. All right, so here's Desmos. Now, I'm not going to be able to see the chat room when I'm over on this because it's in the same web browser. Do apologize for that. If you need anything, please shout in chat. Let me get up into here. Alright, so I'm going to erase what was in there before. And I'm going to do f of x. And I'm going to copy the information coming across. So give me a second here. So we have x cubed minus 2x squared minus 5x plus 6. So x cubed minus 2x squared minus 5x plus 6. And notice, again, I do not like red as a color. use, I think I'll use Massachusetts green, and I'll give it a little bit of dashing just for some variety. And so we have this function here. Now, Desmos is really nice. We can type in the function that we want, and it graphs it. And things to look, if you want to get the powers in there, down below there's this little keyboard function that you can pull up, and you can get the higher powers in if need be. But also if you hit shift, the number 6, which is the up arrow, the kind of the caret, I think is the technical term for it, that will automatically put powers in. And in the worksheet that I sent out, it shows the keyboard shortcuts for doing divisions and powers. And so this types in almost exactly like a calculator. If I were entering this on my TI 84 or my TI 30, I would do X, the up arrow 3 minus 2, X up arrow 2, and I would get these, and that is the one for the shift 6, the caret sign. Now, if we come to the graph itself, I can move the graph. I can use zoom keys if I want to zoom out to see the behavior at larger points. And I can, holding down my mouse, move the graph so that I can center it. Now the book talks about this in terms of graphing calculators, and it calls it the viewing window, and you can set the size of the viewing window. In Desmos, the negative and positive lets you change what you can view, and you can bring it across. Now, let me switch back to the question that's coming here, and it says, identify the x-intercepts and approximate the turning points, and then use the turning points to approximate any local extrema. So I'm going to come back to the graph here and show you how we can do this within Desmos. So coming back here, Desmos lets me click on the graph, and if I click on the graph, it automatically highlights the points of interest. It shows me the y-intercept, the x-intercept, and the extrema or the turning points. So notice this function is a third degree polynomial, so at most it should have 3 x-intercepts and 2 turning points, and this one does. And so if I look here, my first x-intercept is at x equals -2. My second x-intercept is at x equals 1. And if I click on these little gray dots, it holds the point values up. And so my third intercept is at x equals 3. And if I look at my extrema now, or my turning points, I have that the x value is -0.786, and this is definitely a local maximum. And the maximum value the function can take at this point is 8.209. And I have at the x value of 2.12, I have a local minimum, which is -4.061. And so Desmos, I find, is a really good graphing calculator, especially when we're trying to figure out what these functions are doing and looking at the function behavior. It's fairly quick, and it highlights the key points of interest. And almost all of the homework, I wouldn't even say almost, so far I haven't found a piece of homework that I couldn't do using Desmos in the web browser to come across. And I strongly encourage using any graphical software. Now, if you have a graphical calculator that you're comfortable using, or you want some pointers on a graphical calculator, email me. But I'm going to do all my examples using Desmos in the web browser. I find it is a very capable utility for the type of work we're doing. And so if we look at the approximations the book did using their graphing calculator, they've got the same answers that we saw coming across. And so we're able to find the turning points and how they are local extrema, and putting the values back out. All right, now here is an example, and I'm going to do this the same way. And so they're trying to get you to go, hey, what's the leading coefficient, and state the big N behavior. And notice how they wrote this backwards. It's 2 plus 3x minus 3x squared minus 2x cubed. This is perfectly fine. The terms are there. But I think for consistency, it's much easier to write this term first, because this value is what's telling us all our big N behavior. And so I would rewrite this f of x always as negative 2x cubed minus 3x squared plus 3x plus 2. My powers of x decrease. Powers of x decrease, and I can focus on the leading coefficient. So now I can say, hey, this is odd, and it's negative. So it's going to start at negative infinity. It's going to do something in the middle, and then it's going to start at positive infinity. Just keep saying that backwards today. It's going to start at positive infinity, do something in the middle, and end at negative infinity, because I can see the leading coefficient has a negative sign, and it's an odd power. Right, let me come here, come back. And that is everything for section 2 in the book. All right, so what I'm going to do now is I'm going to take, let's see, it's 7, 6. What I'm going to do is I'm going to take about a 15-minute break. I'm going to say, I'm going to reset everything. I'm going to send out a new link so that this video gets recorded at just section 4.2. And then we're going to come back in and we're going to look at section 4.3, which is dividing polynomials. So I'll break this into 2 parts, just like the day class had a Tuesday and a Thursday lecture. I'll break this into 2, but I'll break it right around section 4.2. So we'll come back in and we'll look at polynomial division, which drives most of what we'll be looking at here. So I'm going to end this stream, and I will send out a link to another stream, and I'll start it at 7:25, 7:30.